So I was asked to give a talk, tips and tools to your reduced data, which is an extremely broad topic. I waited too long, and the screen saves. So it's an extremely broad topic. Of course, the tools you need to work with your reduced data depend on the science you're trying to do with your reduced data. But hopefully I cover some useful tools, somewhat from the perspective of what I do, which is spectroscopy. So the first thing, which is something of a message from this whole workshop, underlying lots of things, is that your time is finite. So you shouldn't be trying to reinvent the wheel in your PhD, though maybe you are actually, the point of your PhD is to reinvent the wheel that you're interested in. Sometimes it happens. And hopefully someone has already created the tool that you need to do the thing you want to do, hopefully. Again, maybe your PhD is actually an event that create the tool. And you should be trying to script everything you can. I say this, and then I'm going to show you TOPCAT, which is somewhat inherently unscriptable, but it's never fun to try and recreate plots and things 6 months later. Though sometimes you script stuff and then you run the script 6 months later and it fails for some unknown reason, which is always fun. And the last little tip I have here on this page is you don't be afraid to use something other than what your supervisor suggests as a tool, because your supervisor may be out of date. Of course, this depends on your supervisor and whether they wrote the program they're telling you to use, in which case you should be using it. It's probably a pick your battles moment on this, but sometimes your supervisors are out of date. It may be a case that the tool that's suggested for you to use is something they've just found on the internet one day, or someone told them about a conference. So don't be afraid to use other things. And as I said, there are many tools for working with your data. And when I thought about it, I guess there's tools that maybe you don't necessarily think of as for working with your data, but they are things you are helpful in the sense that people have observed your object before, probably, or your class of objects, and so there is information that exists to add value to your data. So things like Sinbad and Vizier and Aladdin, for Sinbad for looking at basic data about your star, Vizier for looking at catalogs about your objects, Aladdin for just plotting it on the sky, 3D dust maps to actually work out reddening. These things all help you add value to your data. And then the other sort of types of things are, and there's probably some crossover and overlap and fuzziness between all this, but there are tools for working with your data in the sense that you've got some numbers and you want to plot some things up. So things like TOPCAT and Mars and Python, which I've shown. So what tools do I use regularly? I use Python, which unfortunately Anthony's going to tell you all about that, unfortunately, but Anthony's going to have a talk after this, which is all about Python. So things, if you use Python, you'll know all these things: NumPy, SciPy. A couple of things I find really useful are Jupyter, which is what IPython notebooks are now. Well, it's complicated. IPython notebooks are still a thing, but Jupyter is a thing. You might you'll come across Jupyter IPython notebooks using Python to some extent. And there's AstroPy, which is a group. There's a whole lot of Python packages for astronomy things, which is really useful, and Pandas, which I'll show in a couple of slides. And if you use Python, you'll know these things, but AstroPy's going to have a talk. Python is free, and it's free as in beer and free as in speech. What I mean by that is that it's free as in it doesn't cost you any money like a free beer, though there's no such thing as a free lunch, which is and it's free as in speech in the sense that it's openly licensed usually so that you can do what you like with it, you can see the source code, play with it yourself. And there's lots of pre-existing libraries that do things very quickly. Stuff like SciPy and NumPy are written, lots of the functionality is actually written in Fortran and C, very quick. People have spent a lot of time making things run quickly. So I thought I'd mention Pandas. And Pandas is a package that gives you a data structure that they call a data frame. So I've stolen stuff here from their website. So Python has long been great for data mining and preparation, but less so for data analysis and modeling. And Pandas helps fill this gap. And you can do this: you can do your entire data analysis workflow in Python when you can just switch to something like R. So I'll give a little example of something I find really useful in Pandas. So Pandas have this thing called a data frame, which is one of the really useful things about it. It's a mixed type array data structure. So And NumPy, your whole NumPy array has to be the same thing. Everything has to be strings, everything has to be floats, everything has to be its, whatever. But in pandas, you can have mixed types. You can have one column that's strings, another column that's float. You can give columns names. So some of this exists in NumPy and AstroPy tables, but I just use Python about pandas because I like it. But you can give things column names, you can refer to them with strings. There's an index column. And so they've just set up this random table where you have columns A, B, C, D, and column A has foo and bars in it, and B has 1s and 2s and 3s, and C and D are just some random numbers. And then you might have a situation where you want to find the mean or the sum or the median of column C and D for all the situations in column A where it says foo or bar. And so you can just do this on one little line in pandas. You say data frame.group by column A sum. And now it gives you the sum of C and D where column A was bar. And you can give an arbitrary function if you wanted to. You can just define, it doesn't have to be a median or a mean or a sum. You can just give it another function that you've created to do all sorts of interesting maths to these columns. And you can do it for multiple columns as well. So now you've got all the situations where it was bar in 1 and bar in 3 and bar in 2. Where I've used this is, the sort of situation you could use this in astronomy is a situation where you have a giant table of multiple observations of stars, objects, and you've got multiple entries of every star in there, and you want to find the mean radial velocity or something, and so you can just do this in one little line. It's really quick. So, sorry?
Yeah, does it have a bit of missing data?
It knows to do NaN. It does NaN sum or NaN mean. It doesn't.
It skips with and maintains the index and the average.
Yeah, so it doesn't have problems with missing data. So that's why you should use NaNs, not 999s as well. People use 999s or minus
99.
Yeah, it's so frustrating because it screws up sums and everything. You just mask it out. Another really useful package I've come across in Python is this uncertainties package. So this may be not something we do now so much, but sort of if you think back to your first year physics courses where you're expecting these labs to propagate uncertainties through mathematical functions, and was always a pain because you can do everything in quadrature and everything. So this uncertainties package does this propagation for you. So it has this U-float structure where you say 3.1, 0.1, so that's just 3.1 plus or minus 0.1. Another random, make B, which is 4.7 plus or minus 0.5, which is B. And then you just can do maths. You can say, what's A plus B? What's A minus B plus B? A minus A plus B? What's B squared plus cos A? And it just works it out for you straight away. And does all the right uncertainty propagation. Follows all the rules. And a really useful thing I find is that we have a situation where effectively you're subtracting the same thing from itself, so A minus A. It knows that this is 0. So it doesn't try to make it 0 plus or minus something. It's 0. So what you'll see here is A minus A plus B is just equal to B, 4.7 plus or minus 0.5, which is equal to B. And also has a NumPy-esque structure as well, so you can have uncertainties in a NumPy array. There's a bunch of ways of doing it. And you can do cosines of elements in the array. You can find the mean of your array. It's really useful if you've got a situation where you're propagating uncertainties through some complicated mathematical function. You want to get an answer with an uncertainty. And I think the other other tool I mentioned from Python, and this isn't actually necessarily a Python thing, but there's a bunch of different implementations of these Monte Carlo MCMC things. So MC is, as it says here, MC is an MIT licensed pure Python implementation of Goodman and Ware's F-invariant Markov chain Monte Carlo ensemble generator sampler. Basically, this is something really useful for fitting a model to a noisy data. I won't give any examples of this straight away on here because it's somewhat complicated. As I say, there's a bit of a learning curve in the sense that they use a bit of language in there. With these things, there's a bit of language they use that's unobvious what they mean. They'll talk about priors and posterior functions and things that they're not necessarily obvious that they mean. Like a flat prior is basically just telling the thing a range of values you're expecting the thing to have. the other thing I'll say here is that if you use this, you can then put Bayesian in your paper title, and everyone loves things that are Bayesian or Bayes thing now.
A few people really hate it though.
Yeah, if you're a frequentist then. So there's an example. If you go to their website, they have an example for fitting a straight line to noisy data, which seems like a really basic thing, but it's a great example, and it shows you how to build up to. You can use this to build to a slightly more complicated model. The one thing I'll say about this is you need to have a model that takes a very short amount of time to generate. So if you've got a model that takes a second to generate, that's way too long for this, because you'll do like 50,000 model generations in an MC run, and so you don't have 50,000 seconds to play around. Especially when you're starting off, you don't have 50,000 seconds to sit there and see what's going wrong. And there's some other aspects that are awkward. There's a couple of things called the burn-in time and the number of walkers you run with this language they have associated with this. But they'll say there's no good way of working out the numbers for these. They'll be like, oh, if you get a bad answer, try doubling the number of walkers. And if that doesn't work, then double it again and keep doubling until your computer runs out of memory. They actually say this. So it's really useful. You probably want to devote like a week to working it out though. So that's enough Python, and he's talking a bit more about this after me. So some other random tools. So Mars was something that, I've forgotten his name, it was in this room yesterday talking to DFTR. Sorry?
Matt Owens.
Yeah, Matt, yeah. So this was something he showed yesterday for people in this room. It's a really useful tool for finding redshifts or radial velocities for your spectrum very quickly. So it's a completely browser-based thing. Make that gigantic. So it's a completely browser-based piece of code, which is really useful because scientific software is usually impossible to compile and install on your own computer because the person who created it does it in Fortran 77 and you only have Fortran 95. So this is all done in the browser. So you can grab it and put it on your own computer. So you just drop in, say, an A-omega spectrum. So we'll grab the example that they provided. So you drop it in, and in 5 seconds, it has calculated a redshift for 28 spectra. And you can go and look in the Details tab, and you can see the green is the spectrum of the star, of the quasar in this case, and the red is the model. So there's a bunch of different templates that's fitted. So it's saying here that it's found a fit for a quasar with a redshift of 1.18, and also gives you the top 5 other guesses. So it's like, oh, maybe it's a quasar at 2.9, or it's a quasar at 4, or a high redshift star-forming galaxy of these sorts of numbers. And you can go through and you can either accept this first answer it gives, or you can play around with it, so you can adjust the redshift if you wanted to. It has a whole bunch of really useful functionality. It sort of is very clever at getting rid of continuum things. It works really well. And then you go and you can rank things and you go, okay, I accept this as a good one, and we'll go to the next one, and you go, oh no, that's an impossible one. You can work through each one individually, and then you can download a file out at the end. So it actually works for stellar things as well, not just galaxies. The catch being that, of course, it tells you a redshift, and stars have redshifts of like in galactic things. The galaxy stars have redshifts like 0.0001. So I was playing around with this for working with stellar stuff, and I had to go into the code and tell it to return a radial velocity on a redshift. It's all written in JavaScript, so it was a wee bit impenetrable to me to some extent, places, but it works really quickly, really well. They use this in OSDES, and they use it in Taipan, I think. It actually is used in real surveys. Real people use this, and it was all written by a PhD student. Well, it's based on another piece of software, but the PhD student, Sam Hinton, wrote the whole thing.
Question? The database for all the spectral lines? Where does he get that?
So there's bunch of so it has these templates that are built in. So there is some stars, so it's an A star, a K star, an M star, G star, early type. There's 12 different models that it has in there. But if you download the version and play with it yourself, you could put in your own models if you wanted to. Thing about it is that the templates have a resolution that matches the resolution of the spectrograph that the surveys are using. Mm-hmm. So if you're using high resolution spectra, then these templates are blurred compared to your spectra. So you could go and put new ones in. The other thing is you can turn on and off templates as well. So if you really know there's no stars, or you really know there's no galaxies, you would turn off the ones that are wrong, because otherwise it will try to fit a transition galaxy to your moving star or something.
So the data should always be in a fixed file, and like is there dimensions over there like when you run?
I'm unsure. So I think it is somewhat expecting a FITS file. The application it's designed for AAO to some extent, and it will also accept CSV files containing staples. I'm not sure. I've only ever given the FITS files. Because it's designed for Gamma and OSDES, which are AAO survey things. But I've dropped in Hermes Spectra, which of course is AAO. Maybe to some extent expecting AAO things, but I'm unsure what would happen if you dropped in another observatory spectra. Though it's probably only really looking at like the wavelength information, as long as those are labeled in the right ways and FITS header, it should do okay. Sometimes those are good different names. Okay. So that was Mars. I just had some examples of the page in case the resolution was terrible. So another bunch of things is when you've got stellar spectra, so I'm used to stellar spectra, and you want to get abundances out. And there are a bunch of different codes for this. One of the codes I use a lot is called Moog. And this is an example of something that was written in 1975 by someone in their PhD in Fortran and still used today. I don't have an example of this. It's just that there are a bunch of different tools that exist for taking equivalent widths of stellar spectra and turning them into abundances and stellar parameters and everything. And Moog produces plots like this, which is a bit hard to see on the screen, but you've got the white dots of the observed spectrum, and then you go and say a bunch of different stellar abundances, so changing carbon, nitrogen, neodymium, TBNT, and I can't remember what they are. But you can go and see that as you change this abundance in the stellar, in the star, the spectrum changes, and you go and find the one that works best. There are all these different surveys like Galar, which I'm involved with, and ITSO, which is a similar one in Europe. We're observing lots of stars. A lot of them use things like Moog to do their abundances, but on top of it, they've written some very clever codes to do everything automatically, because you have a million stars and you're not doing this by hand. Okay.
I'll just go back to that. It was a really useful tool then. If you were to mention that, say, in a paper that you write, in terms of citation, would you cite that in a particular way?
There's usually, for Moog, the usual way people reference is they reference Chris Needham's PhD thesis from 1978 at the University of Texas in Austin or something. But it's an important point actually in general that you should be referencing your software. If you talk to Nuria, who is an AAO here, she will tell you explicitly that people are not given enough credit for the software they write.
A lot of pages will have something on the page that says, please reference as.
Yeah, so there'll be a paper. In the case of 2D FDR, there's astrophysics. There's a software library that exists now where software is going into, and there are these references that you can put to them. But yeah, make sure in your papers you acknowledge the software you use, because people spend a lot of time on it.
There's a great website called the Acknowledgement Generator, and you just put in what you want to generate, and it will produce standard citations in latex, and just cut and paste that into your paper. I'll put the
Yeah, that's great.
So, but it's a good point that not only reference the papers, the science that you're talking about, but if you're really using a piece of software all the time, put in acknowledgements or reference the paper they tell you to reference, because it helps people get jobs, because then they see, well, they have an impact, a higher impact, they have a higher H factor in everything from the citation. Okay, so this is another another thing I've come across recently. I was dealing with stars that were in the galactic bulge, and I wanted to know how much reddening there was. So this is a tool. So there's a bunch of different. TOMAS have a tool for doing this, and the NASA Extragalactic database have a thing for doing this. This is one I came across because it looks pretty and updated. So it's a website, argonaut.skymaps.info, and it's a 3D map of interstellar dust reddening using 800 million stars from Pan-STARRS 1 matched to 200 million stars from TOMAS. So what you can do is, if you want to know the reddening in a certain direction in the galaxy, you just enter these coordinates in. You go, so what's at 45, 70, we'll soon find out. And it returns a plot that may not be the most exciting plot in this case. But so you can then put the mouse over this, and you say, okay, so at 1.5 kiloparsecs from the sun, the EB minus V is equal to 0.011 plus or minus 0.03, which is the same on both sides. So this is useful for stellar things, because there's lots of reddening maps that are for extragalactic targets where all you care about is this final answer over here, because you care about all the dust between us and it, and it's going to be in the galaxy, or our galaxy. But there's situations where you might be looking at the objects inside our galaxy at some distance that they're in the middle of this. This one's not the best one. Try 12. Oh, this one's a bit more exciting. So you can see that there's different distances from the sun. Suddenly you get a bigger reddening. It has these postage stamps which haven't come up very well on that screen, where you can look and see the general region around. You can also do these in equatorial coordinates if you wanted to. And it has an API, so you would go into a Python code and you would paste in this chunk of code here, paste it in, and then you can just go query coordinates, and it returns a structure called a Q, whatever you want to call it, called a Q result, and it contains all the information you would need to break up these reddening things. And you can give it multiple pointings if you wanted to, so not just one pointing.
Sorry, but if you just go back to that plot, the last plot, you just take that first. Any of them. So if we're looking at all those faint traces in the background, that gives you some sort of an idea of the different plots that we use to.
Yeah, so there's a whole paper on this. There's all these different samples that was made along that line of sight, in that little region of space. You can't actually see it at all on the area. You can see it on my screen, but up until about, can't see the ball here. So very faintly, you might be able to see, sort of, it's like hashed over here up until this point. So what it's saying is, up until that point, there are the number of stars is low, because of course you can't work. It was based on stars between us and a distance. Sure. And if there's no stars in that place, it's very hard to do it. So you can see there's huge uncertainty, and so it's pretty useful for seeing the distances that it can't tell you an answer for.
Which was the next question in terms of uncertainty. How do you derive it?
Well, that's what this number here is. So you could say that for a distance of 0.65, it's saying the EB minus B has this uncertainty. Based on the scatter, and it's doing Bayesian MC kind of things to work these out.
Very good.
So it's useful for getting uncertainties, which we should be caring about.
So is this like accepted in the community as being a good way to actually grab the numbers that you just said and use them?
This paper is only from it's based on a paper from last year. Just trying to think of the names of the paper. So Sheffley is a name that does this sort of work. So the second author is a person who is well known for doing dust maps. So it's all the right sorts of names on the paper. Because of course that's one of the things that can be awkward is that you go and look at the paper and it looks really, or you find some tool, something that looks really authoritative, but it may not be accepted. Well, the other catch is you could go and submit a paper and then the person who's refereeing your paper is someone who hates that person.
You soon find out that it gets rejected.
Yeah. Fortunately, you can go and tell the journal not to have someone as your referee, but you have to give a good reason other than this person disagrees with me fundamentally.
They usually accept that. Yeah.
It may depend on...
We have a long history of disagreement.
It may depend if it's a thinking like 2 big surveys that can disagree. That you might, Okay, so this is a whole bunch of things for, like I say, adding value to your data. Simbad for looking at individual objects. Vizier for looking at data, like catalogs, and Aladdin for plotting things on the sky with a bunch of different things. I was surprised Andy was surprised that Vizier was an Arabic thing, because of course it's Simbad, Vizier, and Aladdin, which are all was it 1001 Arabian Nights? They're all things from that. They're all named in that way.
Just one thing on that. I mean, I've looked at some of the objects that I've been working on on a daily basis, and they seem to be at variance with some of the papers I'm sort of reading. So in terms of approaching these with caution.
Well, they will always have a reference. It's this problem of
Just because it's in there doesn't mean...
No. It could be based on some big catalogue. They're trying to be as modernist as they can to some extent. They'll be looking at large catalogues and large surveys for the answer, as opposed to one little person's paper on that one star.
Yeah.
Because they want to be homogenous in their answers.
Yeah, you can always try to trick it yourself if you can, right? Actually, I just wanted to, before you get too far away from dust, if you are at larger distances, there is a Python one-liner for labels as well.
Yeah.
So there are other things that you can put in if you're at the right distance to check and just compare and have one value.
So I just did some screenshots because I wasn't sure if the resolution of the thing was going to be okay. So this is, if you've never seen Simbad before, this is the sort of page you would get. You put in a thing like that Barnard star, and it tells you coordinates and tells you velocities and parallaxes and different magnitudes. This is something you get from Vizier. So you put in a thing like 47 tuck, and you can see all the catalogs people have produced for 47 tuck, or mention 47, actually catalogs that have objects within some distance from 47 tuck. I can't remember the exact numbers. The useful thing to look at is these little plots over here, which show you the sky position or the sky distribution of the objects in your catalog. Because almost always when you put in some object, it will return things like the Inishikaya source list and the 2MAS catalog and all these all-sky photometric surveys that just everything, they're all over the sky, of course, so there's always going to be an object in them near your thing. So it's useful to look at these things to see the distribution of objects on the sky to see what it looks like. So ADS seems obvious, but just to remind you that we find other people's papers, add value to your data by looking at what people have done. They actually have a new interface called Bumblebee. I have no idea why it's called Bumblebee. It's got useful features such as full text searching, filtering, and it's modern looking, which is always nice. So this is just the page. So it's got a single search form, and you just enter things in this sort of structure. When you go in there, you can filter by year very quickly. You can filter. We'll go there. Takes a moment to load, so we can go log, David, And if you forget to put this as an author, you can just click there and it will make an author for you. So we can go into there, returns all the papers, and will tell us some number at the top. There's 518 papers with David Fogg as an author. You can then quickly filter by co-authors if you wanted to and find the numbers of papers. I'm not sure why you'd ever want to, but you can filter by the grant or publications it was in, keywords. So if you clicked on, say, surveys, you can limit these papers to surveys. You can sort by citation count. You can quickly limit by year. All these things that they existed to some extent in the old interface, but they weren't as quick. So there's a new interface for APS that they're going to be rolling out. So a couple of other random things that I'm unfamiliar with, but look nice because I don't use them because I don't do extragalactic things. So NED, so it's an extragalactic equivalent of Sinbad, has dust maps as well in there actually as well. Astrometry.net, which I've never used successfully, I should say, apart from the one time with their one example on their front page. So this is, if you have a picture of the sky and you have no idea where it is on the sky or you don't trust the coordinates, then astrometry.net could help you. So basically you just give it an image and it will run away and come back in 5 minutes and tell you, oh, it's here, this is where it is. And it will tell you the center of it and it tells you things about the area in the sky, the pixel scale, and it actually will update the WCS, the World Coordinate System information for it. And it doesn't have to be, so this image that they sort of give on their website is one from Flickr. It's just some person's image of the sky and it can work it out. I'm not sure if there's some key to the size of the image or how bright the objects are as to how well it works. But it's useful if you want to get updated coordinates because sometimes you need things really precise. Well, obviously, all the time you need things really precise. Source extractor, which is the worst name in the world. So I think Lee mentioned this the other day. This is for photometry of extended sources. It is the industry standard object detection. This is probably the situation where when your supervisor says to use it, you use it. You don't try and do something else because this is the thing for doing it. Okay, so that's all the random tools I've mentioned. Does anyone have any questions?
Sometimes you've got the statistical package there, Panda or something.
Yeah, there was pandas and panda. Not sure why I'm scrolling at.
Do you actually use any of the other ones, like the R?
I've never used R. I grew up in a place that's rolling R's.
Fair enough.
No, I've never used R. Does anyone use R? Caroline uses R.
R.
Yeah, so there are other languages to use. R is very good for statistics. Have never had to leave to some extent. And so that, of course, this is their nice advertising blurb that they say, oh, you can use pandas instead of R.
All right.
Yeah, they actually say, switch to more domain-specific language like R. And the other thing about pandas, I should say, is that it has a lot of functionality. Like it's like SQL, it does joins with, if you're used to SQL, there's very similar language about inner and outer joins and things. So, any other questions?
I think you can link to R from Python.
Are data frames saved as binary files, or are they straight?
You can output them as whatever. There's a whole 10 different out functions. So you can save it to a CSV file. You can save it to. You can pickle it. You can do whatever you want to with it. I tend to save things as CSV files because I like a file that I can look at in a text editor.
It might get too big and too many.
Yeah, that's one thing. Yeah, that is one aspect of CSV files. There's a problem that when you load them into Python, you have to wait. Yeah. And actually, that's something I haven't bothered here, but about IPython notebooks. Why you should be using IPython notebooks when you're playing around is that you can load, if it takes a while for your data to load in, like it takes a minute, you can load your data in and then play with another tab, other cells, without having to load that data every time. So if you're running a script where the data takes a minute each time, you're testing something, it takes a while. Okay, so I mentioned the TOPCAT is another thing I use all the time. So TOPCAT, his name is Tools for Operations on Catalogs and Tables. It's another example of astronomers' acronyms. So do you have tabular data? Do you have tabular data? Need to quickly make plots, cross-match your data with other tables, create subsets in your data by drawing on plots. But sometimes in a situation you've got a plot and you want to work out what stars are or what points in your plot are, and you want to draw a circle on them, get them out, and you can't do that in other things because you can, but TOPCAT does really nicely. TOPCAT is something you should be using. So I thought I'd run through a little example of finding globular cluster stars in RAVE. So after the experiences of yesterday and getting code not working, I thought what I would do is I'll run through it, and if things don't work, we can look at it after in the break, but if things don't work or you can't quite follow along, I can talk to you afterwards, but we'll sort of play along. We'll see what happens. So you can load TOPCAT and you get this window that looks like this, which is unexciting. So we can load in a large table. So if you can find where we put RAVE DR4. So one thing I should say about TOPCAT, and it just reminded me about CSV files. So this file has 482,000 rows in it, and it loaded in no amount of time. And that's because it was in a FITS format. If it was in a CSV format, TOPCAT would actually take a while to load it in because it would be loading the whole thing into memory. But because it's a FITS file, TOPCAT just keeps it on the hard drive, which is useful when the table is large. So just to explain what the RAVE survey was. So RAVE was the radial velocity experiment. It was a spectroscopic survey at the UK Schmidt at Sunny Spring to observe 482,000 stars in the Milky Way to get their radial velocity and see what the galaxy looked like. So, and this table is now loaded up, and you can play around. You can sort a column you can sort it by columns. You can see that now we've got the radial velocity of like -1,000, which is kind of crazy. You can hide columns if you wanted to. You can move columns around. So you can do all sorts of little useful things in the table view. But what you might want to do initially is just to see where these things are on the sky. So you press the sky plot button and nothing happens because TOPCAT is being silly about this. So TOPCAT hasn't worked out which one's the right section of the explanation, so tell it. So now we have 482,000 data points being plotted dynamically. So this is another useful thing about TOPCAT if you have a large data set, is that if you did this in Python, you would have a ridiculous file that would take forever to try and render in your PDF viewer. But TOPCAT is quite happy to plot these because it's not really showing all the data points. So you can zoom in and you can see it goes a bit silly. It's just every one of these data points is a star. And we can just zoom out again. So this is just the scroll bar, the two-finger scroll on my touchpad. It could be other things on your computer depending on how you set up your computer. The other really useful thing in TOPCAT is if you click on a random data point, so we clicked on that data point there, it highlights the row in the table that data point corresponds to. So if you've got a situation, this happens all the time, you've got a plot and you want to work out what data point you're talking about, you can find it easily. It also works the other direction, but not quite in the same way. So if I click on a random row in the table, it will have illuminated that data point somewhat. Here it is. It illuminates or highlights the point in the plot, but doesn't take you to that point in the plot. I'm not sure why it doesn't do that. It doesn't work both ways, but it is what it is. You can, so that's one, so clicking on data points and seeing where they are in the plot, the tables is really useful to me, TOPCAT. The other really useful thing is defining subsets. So you have a situation where, zoom out again, so there was this there's a group of stars over here that they've observed. Like, what's going on here? So you zoom in and you say, that looks interesting. Looks like there's a clump of stars in the middle of this area they observed around. So which ones are these in the table? So you could sit there and individually click on each one, see them in the table, or you can define a subset. And so you can just literally, you can click on that button up there to draw a region, and you go, really sometimes hard with a touchpad, and then you click on that button again, and you say, interesting, the name, quickly, add and set subset, and now in the data table here, we're only seeing those stars. And you can here, so suddenly you can see there's only 191 rows visible. And you can go, because it's the rate of velocity experiment, I'm assuming this is a cluster of stars to observe, so these things probably have a similar rate of velocity. We can put a histogram up, HRV, which is the velocity, and I can zoom in and find there's a group of stars that have very similar, there's a clump of stars with a similar rate of velocity here. And then you can zoom in a bit more. We can actually define a subset from this plot. Vaguely, we'll just guess roughly. So this is velocity clump. And subset. Now you see over here on the plot in lots of colors, so I'll make it color velocity clump. So now you can play around, you can change colors, you can make the data points bigger. So now you can see that the ones that were in the little velocity clump tend to be in the middle of the plot. So it's probably a cluster. So any questions so far? It is extremely useful. So the one catch I should say, so we've identified this interesting thing, but you can't really easily work out what it is from inside TOPCAT, because obviously it's a cluster of stars. So what we can do is go, now if you have a ladder installed,
just a quick question on TOPCAT. You can have any labels in the fit file, and then you can view it as any arrangement of those labels that you want.
You mean the columns?
Yeah.
Yeah. So literally you can just go scatter plot. So you don't have to just do it in the sky. Sky plot's useful.
Yeah.
But you can, so you literally can plot your right ascension against your velocity or against the error in the velocity. You can plot everything against everything.
Exactly. Okay.
That is one of the most powerful things about it is it's so quick. So if I turn back on, we're only seeing the interesting. We turn back on. So that is all the data points again, and then we can just quickly flick through everything against everything.
That's great.
So it's really useful for situations where you have no idea what you want to find.
Yeah.
Which happens. You have no idea. You have no idea. You've got 20 elements for star. You don't determine the elemental abundance. It's like 20 elemental abundance is like 100,000 stars. You have no idea what things are going to be interesting when you plot them up against each other. So TOPCAT and Aladdin, just to show this little useful thing that we go to here and make that. So what you can do is you can actually link TOPCAT and Aladdin. So there's a little button that appears illuminated now, and I click this, and it sends the coordinates of those stars to Aladdin, and then I can go into Aladdin, let's look at my own screen, and click image, produce a sky, optical, DSS, solid. It'll take a moment.
Yeah.
There we go. So we can actually see where our stars are on a plot on the sky. And you can actually see there's a cluster of stars there. And TOPCAT, Aladdin has a useful feature that if you go to Tools, if you turn on Sinbad pointer, what it will do is when you just hover the mouse for a while, it will find the closest thing in the Sinbad to where you are. So if I move it to another point, it'll actually say something useful in a moment. So it now tells me that this is NGC 2682, which I can go and Google. NGC 2682 and find SM67, which if you know your galactic globular cluster, open clusters, is one that people use all the time. It's solar type dwarf stars, so it's fantastic for those sorts of things. The other thing I'll just show very quickly is getting Vizier. So you can actually go, there's a load tables directly from Vizier into TOPCAT. So if we search by keyword for particular, so Harris, grab a table that's going to be useful for this. So there's a table called globular clusters in the Milky Way. A slightly annoying thing about loading tables from Vizier into TOPCAT is that you have to accept that there's no fine control over the columns you get. So you have to make sure that you probably want to go all because you want all columns. Sometimes it doesn't give you useful columns. So we can load that in, and we have that table now in TOPCAT to play with. So this one is a catalogue of all the globular clusters on the sky, because what I want to do is find all the cluster stars that may have been observed by Ray. So the obvious thing to do is to find all the stars that are within, or to find all the stars within 1 degree. Find all the stars within 1 degree of a cluster in Ray. So we just go into here and we cross-match sky 1 degree, Brave, and we make sure we take coordinates. Ferris catalog. We want to do all the matches. So we're about to positionally match a table of 482,000 rows against a table of 147 rows, finding all the matches within 1 degree of each other on the sky. And there's no row count because I forgot to tell it to do everything. So if you've ever tried to positionally cross-match in other things, you should be using this because we've got the answer. It's so quick. And then we can plot up, say, the velocity of the stars against the velocity of clusters, VR, and there's a lot of noise in there, and so we plot a straight line. So then you can see that there's a group of stars here, this is just a one-to-one line. You can see there's a clump of stars there, and a clump of stars there, and a clump of stars there. Zoom in, we can make them a subset, cluster, it's here. And so we've found 16 stars from NGC 3201 that were likely observed by Rave because this thing has a really high velocity, so they're obviously cluster stars. I'll stop there because you can just keep doing things when you're TOPCAT, but positional cross-matching, creating subsets. You can do all sorts of subsets. You can find subsets mathematically with logic, so you could go and say, find me all the stars that have HR. So we'll say find a subset where the absolute HRV minus VR is less than 20. So you can define things with logic statements to find all the stars, and it tells you statistics. You can get statistics on your rows, all sorts of things. TOPCAT is fantastic. So I think I'll finish there.
Great. Thank you very much. Very glad to see that. I'm sure there's probably lots of questions. Yeah.
So like, is there a way, like, I've used this function where you can match 1 to 1, but I wanted to see like the 3 closest, for example. So I tried to do it in AstroPy, but I couldn't work it out. But,
So I don't think there's this TOPCAT, but you could get it to. Maybe pandas would be a way to do it, because you can start doing things in your groups.
Well, if you want the 3 physically closest objects, what you could do is find all matches and then write a logic statement saying, give me back anything within this radius based on distance from your object.
Yeah, but in terms, if you've got multiple groups, it's a bit more complicated if you've got multiple groupings. So when you do the all match,
you probably want to import it into a table and then write a actual script for it.
Yeah.
Okay, just make that all again. So when you do if you do an all match, you actually end up with this extra columns at the end. There's one called group ID, which is these are all the things that matched the same cluster, and then it tells you that there were 14 of those. Then there's group 2, and it's also got the separation column. This column separation is the distance in arc seconds between the 2 sets of coordinates for that object. But yeah, there isn't quite the functionality you would want, which is to only return the best 3 for each group.
but in that case, like group ID 1 will have the first 3 in separation would be the 3 closest.
Yeah, but there isn't quite the functionality to do, because there's like, there's how many groups? It's 57. It's found 58 groups. Yeah, and so there isn't quite the functionality you want, which was to do this for all 58 groups automatically. You could do it manually. It might be one of these things where the amount of time you spend coding it to do it another way would be about the amount of time it would take you to just do it by hand. Which is another thing to think about sometimes. Sometimes it's better to do things manually than actually try and work out a clever way of doing it.
Yeah, you've greatly also expanded your parameter space by this method as well, because you're pulling in more and more data for the same objects. So you can keep going and look for photometry or whatever else you want. And, archives. So, are there any more questions for Kit?
Yeah, one cool thing about TOPCAT is you've got an API underneath which is called stilts, and pretty much any plot that you can generate by clicking around, you can reproduce it with like a 1-line command. I've
never used the language, sorry, but
documentation is a bit of a pain, but I mean, if you need to like reproduce plots in pipeline or something, it's like really easy to do.
And a lot of it's on Stack Exchange, stuff like that too. So if you search for, API, Python, this thing, TOPCAT. Any other questions?
No, that's damn useful piece of
Yeah.
information.
Yeah, thank you very much, Jeffrey.
TOPCAT is amazing.
It's really been great talk.
It's a situation where you don't know what you're trying to find, and it's useful for large data sets. So I could have quite easily matched a 400,000 row table to a 1,000,000 row table positionally and found, or just do the best matches, and it will take 10 seconds.
The fact you can actually integrate into Aladdin.
Yeah.
Vice versa. It's just.
So it's a thing called SAMP, I think is the protocol. There's a little icon that appears at the top of my screen there. And DS9 integrates as well, but it always throws me error. So I'm not sure. It probably is a similar kind of thing. So if you had an image that had a coordinate system associated with it, the WCS associated with it, you could throw your coordinates from TOPCAT into Aladdin or into DS9. Actually, the other thing I didn't show was if I just go back and do interesting, bring up that. Hope this will work. So, and not only does it, when you click on the data point in your plot, will it illuminate the row and the table. When you mouse over a point in Aladdin, it illuminates the row of TOPCATs. It doesn't work the other way, unfortunately. But it's so useful when you have random points you want to know where they are on the table.
Or checking your calibration files for observing, or
The other thing I should have said is that you if you get images from the AAO, you can load them through. You can't get to see the image in TOPCAT, but you can get the fiber table. So if you've got 2DF images, or 2DF Omega or 2DF Hermes raw files, you can just load them straight into TOPCAT and get the fiber table out.
so yeah, really, really useful. We should probably go ahead and stop there. Say, yes, almost infinitely useful. But thank you again. So